So I am one second, let me just put this on full screen. I am a condensed matter physicist by training. Are there any physicists in the room? Oh yeah, there's a bunch of physicists here. So physicists in the room, you might be familiar with this diagram over here. It's an energy diagram of the band theory of solids. And basically what the building blocks of computing currently are transistors, which are based on on semiconductor physics. And transistors can be either on or off. And what that means is that you apply an electric field to change the properties of the semiconductor to become conducting. So this is basically the same as a light switch. It's on or off. And what that means is if you look at a CPU, central processing unit, and let's look on the inside here, is that on this chip there's billions of these transistors that all carry currents that flow through these circuits and do computations. So in the 80s, there were some physicists who thought, hey, actually nature itself isn't classical, it's quantum. So a lot of calculations we do on computers these days simulate nature, simulate physics. And we are now at the point that we actually have to start simulating quantum mechanics. Even transistors themselves are now so small that they're at the scale of quantum mechanics. So we actually are now, to optimize our CPUs, we are simulating quantum physics. And to do that better, why don't we actually create a computer or computational model that is inherently quantum mechanical and takes these effects into account? So hence the idea for a qubit or a quantum bit was born. You might be familiar with this schematic over here on the left, which is the Bohr model of the atom. Qubits were actually inspired by the atom itself. So an atom can be in the electrons in an atom can be either in the ground state or in the excited state. For example, this simple atom over here. In more complex atoms, there's more energy levels. But the idea of a quantum bit is that we engineer an artificial atom that has only two levels, the ground or the excited state. And at Rigetti, we engineer these artificial atoms. As we said, we are a full stack quantum computing company. So you might think that because atoms are really small, that artificial atoms are also going to be very small. So you might be surprised to see that actually our artificial atoms are quite large. They're about 1 millimeter in diameter here. They are microwave circuits, so they're patterned aluminum on top of silicon, so they're silicon chips. There is, however, some secret sauce here to actually unlock these quantum mechanical properties, which is there is a nanostructure here called a Josephson junction, which is about 200 nanometers in size. And we cool these down to absolute zero temperatures, almost like 10 millikelvin, to unlock these quantum mechanical states and control them. These chips are fabricated in our fabrication facility in Fremont and cooled down and characterized in our lab in Berkeley. What you see on the left is a dilution refrigerator, which is the inside of these cans over here that you see in the picture on the right, which cools down the chips to these absolute zero temperatures. There's a little more to qubits than just these zeros and ones. Actually, a qubit can be anywhere between a 0 and a 1. So we can actually represent a qubit on a sphere where the z-axis is the energy of the qubit, so the 0 or the 1, and the x and y axes represent the phase information. So you can see here a sphere with these spherical coordinates where the z-axis, the positive side of z-axis is the ground state, and the negative z-axis is the excited state. So this is typically how you would explain a qubit. It's like a normal bit, except that it can be 0 and 1 at the same time. So this is how you would express a qubit in Dirac notation, using theta, the polar coordinates, and phi. So you might wonder, what does that mean? Why would a qubit be in 0 and 1 at the same time? How do I measure that? So this is, for example, a qubit in this state, a superposition state, 0 and 1 at the same time. Actually, we can only measure the qubit on the z-axis. So we have to collapse the state onto the z-axis, so we can only measure either a 0 or 1. So what we do when we measure qubits is we actually measure them many times. So for example, we take 10,000 shots, and then half the time we measure 0, and half the time we measure 1. So the result itself in classical space is still binary, so I still get 0s or 1s, but the quantum state itself is non-binary, so it has this continuum of states. And so now you might wonder, how do we actually control qubits? So how do I tell the qubit that it's in the ground state or in the excited state or in 1 or 0, so I can actually do computation? So to do this, we send the qubit a microwave pulse. This pulse is configured to be exactly at the resonance frequency of this 0 to 1 transition of the qubit or artificial atom, pretty similar to what you would expect, for example, in an atom. If I would radiate it, it would go into the excited state. And what happens is it oscillates with a Rabi frequency between 0 and 1. Now the cool thing is I can engineer this pulse. I can actually send a pulse with a deliberate amplitude and time. And I can say, okay, I'm going to now send a pulse that rotates the qubit onto the equator, so into this superposition state. Or I can send a bit of a longer pulse and then flip the qubits from 0 to 1. This is what we call a quantum gate. So if I then see even more, then I can go all around the Bloch sphere. So to actually program a quantum computer or program these quantum bits, we have developed a language, QuIL, the quantum instruction language. And similar to a QPU or CPU having gates such as AND, NAND, OR, and so forth, a quantum processing unit, or QPU, has quantum gates. So the X, the NOT gate, which is the gate you get when you flip a qubit from the ground to the excited state, so a pi rotation around the X-axis. Then there's also gates such as Y and Z, which rotate the qubit in phase space, so I can rotate it around the Y-axis or around the Z-axis. Then there's the Hadamard gate, which is a combination of a pi rotation around X and a pi over 2 rotation around Y, so that rotates the qubit onto the equator, into the superposition. And then there's these 3 entangling gates, which I will explain later, which use quantum entanglement to entangle 2 qubits. And the hybrid comes into play where we actually start interacting with this QPU. So this is a very new field. We are actually creating this field as we speak right now, and to interact with a quantum computer is not something that people have done before. So typically, how to translate a quantum program into the classical world is to do a measurement. And to create a quantum program, you actually define circuits. So this is the interface that we provide with QuIL. This is an example QuIL program. So this would be executing an X pulse or a NOT on qubit 0, a Hadamard on qubit 1, and a Z rotation on qubit 1. And a C NOT, which is a conditional NOT, so this is this entangling gate, which I will explain later how that exactly works. What that means is that if qubit 1 is in the excited state, or in 1 state, then it flips qubit 0. And if it's in the ground state, then it doesn't do anything. So this creates this quantum entanglement. And one second. And importantly, we have this hybrid classical quantum interaction here, where you measure the quantum state and save it into a classical register. So you can assign classical registers to the outcome of quantum measurements. So here's a cute little animation of our stack. It looks sort of like a totem, but I'll just explain in steps what all of these layers mean. So on the top of the stack is our pyQuil library. So you see this cute little snake here. This creates QuIL programs. Then when you send it to our API, it gets translated into a pulse program, which does these quantum rotations. It gets sent to the QPU. This gets translated into quantum operations, which then can read out. So as I said, you only measure the z-axis, so you only get 0s and 1s back. This you can then take the average of and save into a classical register, and then get sent back to the user. So I will do a little demo. I will create a program that rolls a die. So I create a quantum die, 8-sided. To create this die, I will use 3 qubits, so 3 bits basically, to encode the numbers 1 to 8. So I basically take the binary value and I add 1 to it. So for that, let me just zoom in a little. Created a Jupyter notebook, so I can program a quantum computer in a Jupyter notebook, which I think is pretty cool. So first, to get set up, I go to our website, rigetti.com, zoom in, sign up for an API key. This is a very simple process. You don't have to fill out any form. You just put in your name and your email. Then you get an email that looks something like this in your inbox. This has your key and user ID in it, which here I've ADSF'd out. And yeah, then you go to your notebook. Typically what you do is you just copy paste this key in here, the key and user ID, and write it to a file .pyQuil_config. You only have to do this once. Great. So now, presuming that you have installed pyQuil, which you can install with either pip or conda, we can start importing some of these programming elements. So a program, which is a quantum program, QVM connection. So first part of this demo will run on our simulator, which everybody has access to. So if you sign up, you can immediately use our quantum simulator. And I'll import some gates, X and H. Okay, great. So now I'll connect to our QVM, quantum virtual machine. And now let's just quickly demonstrate how to create a program. To create a program, and I just apply an X pulse on qubit 0. Then I measure all the qubits. This is just a really nice shortcut here to measure qubits. I can also actually just add a measure command here. Same thing. Oh, I have to import it. And then I can execute it on the QVM. And I will get a result. So as you see, this is a list of lists. So what I mentioned before, to actually reconstruct your quantum state, you have to do multiple shots or multiple measurements. So I can enter trials equals 10. So that's what the inner list is. The inner list is the single shot result. So as you can see here, I flipped the qubit from 0 to 1. So now I can also do a Hadamard gate. So I'm just going to copy this. So I said the Hadamard gate rotates the qubit onto the equator and gives you a 0 and 1 half of the time. So if you would plot this on a histogram, you would see half the time 0, half the time 1. So let's create a quantum die. For this, I use 3 qubits, and I apply 3 Hadamard gates. So I basically create 3 random numbers, 3 random bits. So these are, again, these 8 possible results. Then to roll the dice, so I use this convenient measure all function, so I can just print roll dice. You see that it creates this program automatically for you, where it measures all the qubits and puts it into these classical registers. Just move this up. Great, so now I can roll this die, and it's going to give me a random bit string. And here I extract the die number from this bit string. And I add 1 because I start with 1. Great. I have a quantum die. So now let's run this on a real quantum computer. So for this, I import the QPU connection object. I can see what devices are available as well. I can run get devices. And I think this I have to put use dict as dict to get me a dictionary. So you see here there's 2 devices. One of them is online, the 8Q agave chip. So I'm going to connect to that guy. And again, I'm going to roll the dice. And now it's running on our quantum computer in Berkeley, which I think is pretty cool. So yeah, here we are, quantum mechanical die. And this is the result. All right. Thanks very much. So now to explain, let me just quickly check on the time. I think we're still good. So now I'm going to explain this concept of quantum entanglement, which you might be familiar with, might not be familiar with, but what I really like as an analogy is using 2 boxes. So let's say I have 2 quantum boxes. They have quantum mechanical properties. I can put in 2 cubes in each box. Each cube has a label, 0 or 1. Then I'm going to put them inside of the box, and I'm going to shake the box and randomize this result. And then blindly, I'm going to pick one cube from the left box and one cube from the right box. And there are 4 possible outcomes to this: 0, 0, 0, 1, 1, 0, or 1, 1. And each of them occur with equal probabilities, right, if I just have a normal box. Now, I'm going to do this entangling operation. I'm going to entangle the 2 boxes. The fun thing is now, what happens, I can change the underlying probability distribution of the outcome of these random guesses, random pulls from these cubes out of the box. And now I can actually enhance the probability to get a equal parity of 0, 0 and 1, 1 and completely suppress odd parity. So you might wonder, okay, how do I actually do this? How do I create a quantum entanglement? Of course, I cannot do that with macroscopic objects such as boxes, but I can do this with qubits. So these artificial atoms, I can entangle qubits. By the way, this quantum entanglement, Albert Einstein had a lot of problems with this. He called this spooky action at a distance. The reason why is because you actually, when you get a 0 from one box, this immediately influences the result of the other box. So this means that somehow there is some communication between the boxes, or this is not something that he could understand or accept. So this is a very, very strange concept. And the way that we actually make this happen in the lab, so it's a strange but very real concept. The way we make this happen in the lab is we apply another pulse. In our lab, we call this a flux pulse. What we do is we actually bring the energy levels of the 2 artificial atoms close together for a split second, literally for a few, like 100 nanoseconds. And this creates this interaction between them that entangles them. So to create a Bell state, or this equal parity state that I mentioned before, what you do is you apply a Hadamard gate on one of the qubits, so you bring it onto the equator, and then I apply a conditional knot on the other qubit. This means that if you measure this qubit to be in the ground state, then the other qubit is also going to be in the ground state. And if you measure this qubit to be in the excited state, then the C0 gate will flip the other qubit into the excited state as well. So this is what this program looks like in Quil. So there's another example here that I'm not sure I'm going to have time for, so I'll skip it for now, but you can do it yourself on your laptops. The link is right here. I created a binder repo here, so you can either go to the repo yourself and install it on your laptop, or you can just go to this link, go.rigetti.com/quantum-dice, and there's a few notebooks in there, including the one that I just demonstrated just now. And the way you create 2 entangled quantum dice is you use 3 qubits to encode one of the dice, and then 3 qubits to encode the other die, and then you entangle those 3 qubits like this. So the first bit, the qubit of the first die with the first qubit of the second die, you apply this Hadamard C0 program, and so on and so forth. You'll see that if you randomly roll the dice, you'll always get the same answer for both of the qubits. So I want to briefly go into some applications of quantum computing. The example I showed with the quantum dice is a very simple example, and it only shows a pure quantum algorithm, so it doesn't have any interaction with classical libraries or this hybrid interaction. So what we do at Rigetti is we work on something we call quantum machine learning. So what you see here, this is a paper we published last year where we did unsupervised machine learning on our hybrid quantum computer, on our 19-qubit chip, Acorn. And what we did is we mapped a max cut problem onto our qubit lattice. So max cut means that you have a graph where each node has some properties, and max cut creates the maximum difference between the nodes to classify them into different groups. And what we did to achieve this result is we used a quantum algorithm called QAOA, Quantum Approximate Optimization Algorithm, which is a parameterized quantum circuit. It's parameterized by gamma and beta. And we optimize over this circuit using a classical machine learning algorithm. So this is the topology of our chip. So these are the different qubits, and we map our max problem exactly onto the topology of the qubits. So thanks very much for your attention. To learn more about Rigetti, you can go to our website or read our docs on pyQuil.readthedocs.io. We're also on Twitter. If you have any questions, I'll be here until Saturday. Just reach out to me. I'm also on the SciPy Slack. And yeah, thanks very much. Happy to take questions.
So we have time for questions. Once again, there's a mic there, so you can line up there. And I can also come to you if you have questions.
Hi. Can you remind me how many qubits you have in the cloud right now online? And I'm also just wondering if anybody has done anything like really useful, like with it beyond sort of like educational stuff.
So these are currently the chips that we have available. So this is our 8-qubit device that we released last year. It has 8 qubits in a ring. And then we also have our 19-qubit chip, which we currently only use internally, but it's been up in the cloud available for a while. There have been multiple people who have used our QPU to do research. So quantum information theorists have been running their algorithms on our hardware. So for example, this group from Canada, Waterloo, have done quantum algorithms to train neural networks. This researcher from Switzerland has created a game to benchmark quantum computers. And this group has done work from Oak Ridge National Labs and work on simulating an atomic nucleus. So we're still not at the point where we can do something useful in the sense that quantum computers are not yet faster or more efficient than regular computers. But we are at the point where we can start thinking about these problems and start thinking about when the hardware is at the point that it will reach a quantum advantage, that we have our software ready.
Question over here.
Yeah.
Sustainability, so you're cooling this thing with liquid helium, I'm assuming? So how's that going to transfer as we get more and more quantum computers, given that liquid helium's a finite resource?
Sorry, can you repeat the question?
So I'm assuming you're cooling this thing down with liquid helium, correct?
The cooling is premium? Sorry.
Liquid helium.
Oh, helium. Yeah, that's right.
And so how's this going to work
Yeah.
if liquid helium's a finite resource and it just goes into space?
Right. So helium is indeed a finite resource. Let's just go all the way back. So here it is. So we actually don't use up the helium. We actually recycle it. We recover it. So I don't know if you can see it in this picture, but there are these cans here in the back, these gray cans, or cylinders. And all these tubes coming out here, they're actually a closed cycle. So it's a closed cycle dilution refrigerator. So what we do is we have a mixture of helium-3 and helium-4, 2 different isotopes of helium. Helium-4 is pretty abundant. It's what you use in party balloons and so on. Helium-3, however, is pretty rare, and it's a byproduct of oil drilling, actually. And that is our pressure. So that's a material we recycle. So we pump it through our system continuously. And it does happen sometimes that we lose some helium-3. Currently it's just very expensive. And in terms of sustainability, there have been some theories that there is helium-3 on the moon that could be mined. So who knows? We might go have a helium mine on the moon.
Hey, this is very interesting. I don't know anything about this. I was just curious, is there any sense of how the energy demand of the computer would increase as you have more and more things entangled? Is that modeled? Like, how does that compare with normal computers?
That's a great question. You mean energy demand in terms of the usage of the quantum computer, or you mean in use of
I was just curious if does it take more energy to have more entangled things, or is that not, it does?
Yeah, so indeed, having more qubits takes more cooling power. So we would need a larger fridge. So as you see this brass plate over here, it's about this size. And that can cool down a chip that's about this size. So if we would increase the number of qubits, we would need to increase the cooling power. One other problem with quantum states is that they decohere. So naturally, nature wants to default to the ground state. So this means that qubits, when they are in the excited state, they naturally want to relax into the ground state. And this is characterized by the decoherence time or the relaxation time, which is currently on the scale of about 50 microseconds to 100 microseconds. And then there's a dephasing time, which is the time in which the qubit loses its phase information, which is even shorter, which is about 20 microseconds. So if you want to entangle a lot of qubits, you have to do that within the time that the quantum bits are going to retain their quantum information. And that is currently the bottleneck. So it's not necessarily energy, but it's more the quality of the qubits that limits how many qubits you can entangle.
But the assumption is that you'll be able to decrease that just continuously, or?
Sorry, can you?
That bound is something you expect to be pushing down more and more?
Yeah, definitely. That's definitely something we're pushing on right now. We're trying to extend these coherence times as much as possible. Yeah.
Thank you for the presentation. This is really interesting. I'm recently just graduated from undergrad in computer science. I'm going on to get my master's, and I'm curious as to how someone in higher education can continue to learn about things such as quantum computing, because I'm not sure whether or not these types of, I don't think there's a quantum computing course yet or anything like that. So where could I go to find resources on how to learn about this?
That's a really great question. Currently, actually, a lot of people at Rigetti, we're not all quantum physicists. So there's actually a lot of computer scientists and people with traditional software engineering backgrounds working at Rigetti. One resource I would recommend is our docs, pyQuil.readthedocs.io. There's a pretty nice comprehensive overview of introduction to quantum computing. You can start playing around the examples. You can actually start quantum programming yourself. So there's this binder that I already mentioned, go.rigetti.com/quantumdice. Then there's also go.rigetti.com/pyQuil getting started, I think. Let me check. So this is on my GitHub account. So yeah, that would be my main advice, is to just get your hands dirty and start coding your own quantum programs. Here, pyQuil getting started. Includes also some really physicsy examples, such as this qubit relaxation that I mentioned, where you can actually see the qubit relax into the ground state. There's also some really good books. One book, Quantum Computation by Kitaev, I can really recommend, or Mike and Ike, as it's called, by Mike and Ike, Isaac Schwang, and Michael Nielsen. Quantum computation and quantum information. But yeah, I'm happy to follow up with you after the talk and give you some more reading material. Yeah.
So can, or even how, can quantum computers be used commercially for like the general public and for businesses?
Yes, that's right. Yes, so currently our platform is usable for free. So you can just get your API key and you can use our simulator for free. If you want to use our QPU, you fill out a form on our website to request access. And yeah, you can be a business. It's for academics currently. Oh, sorry. Currently, most of our users are academics, but we also work with companies. Oh, yeah, it takes a while to load. Anyway. We recently renovated our website, so I'm not really sure where everything is. Are there any more questions? Oh, yeah.
Hi, thank you for your talk. As you mentioned, there are physics limits to your qubits, like they have decoherence time, right? So are there any constraints when I write a program for these quantum computers? Anything I need to pay attention to?
Yeah, that's a great question. Actually, one thing that a lot of people run into when they first start writing quantum programs is let me just see here. Is the topology of our chips. So quantum information theory sort of assumes that all qubits are connected to each other. So also if you're going to run programs on our QVM or quantum virtual machine or simulator, you'll see that you can just connect any qubit with any qubit. So a lot of, for example, Shor's algorithm or Grover's search algorithm, they all assume all-to-all connectivity, while in practice it's actually not the case. So if you look at our qubit topology here, which is in the docs, you see that it's a ring. So there's qubit 0 is connected to qubit 1 is connected to qubit 2, etc. So to simulate this all-to-all connectivity, you have to do something called a swap operation, where you swap the quantum states and do sort of like a jigsaw puzzle of quantum states. And this comes with a cost, because you have to do these swaps, which takes time, in which the qubits can decohere. So yeah, that's definitely, so if you're strong in graph theory, this is very much an unsolved issue still. Yeah.
So thank you for your nice talk, and thank the entire set of speakers who gave excellent talks. We have to break now for lunch, so if you have any further questions, I encourage you to meet the speakers directly. Thank you.